the plan is the next 40 minutes or so, we will talk about propositional logic. Maybe there will be some left over the next time. And then this is chapter 2 in your book. And then chapter 3 is later probability calculus, where we basically do the foundations of things. So propositional logic is simple. As I said, you will be using logical techniques throughout. But the good thing about this is the part of logic now you need to know has been simplified to a large extent. So this part today is classical bread and butter. Everybody has to know this. The stuff that we'll be using later is, in a way, even more accessible, because as you'll see, it's all based on circuits as you know them in digital logic. So it's a very nice reconstruction of some of the logical material that is very easily accessible now, and the part that we'll be using. Okay, so what are we going to do with logic? So the first thing to observe is whether you are using probabilities or degrees of beliefs or true or false assumptions. All of these are properties of a proposition, right? So the propositions are the language for, or the way of expressing events. That's constant. And Boolean logic is one way to actually specify events. So what we're going to do is talk about Boolean logic. And the two key things here are syntax and semantics. Syntax is, what does a sentence in propositional logic look like, or a legitimate one? That's part's going to be pretty easy. The second part is semantics. And it is simple, as you'll see. It's not a lot of material, core material, but pretty important. That part you have to break into to have good insights into things. And I know some of you who've taken either Intro to AI or a similar course before have seen this material, but you have to actually do multiple passes at this to kind of really penetrate it. Okay, so let's start with syntax of propositional logic. First, concretely, you have an alarm that's meant for detecting burglaries and may also be triggered by an earthquake. And here's an example sentence of propositional logic: burglary or earthquake. Burglary and earthquake are variables called propositional variables. Now we have a logical connective, the or. Here's another example: burglary or earthquake implies alarm. Now we have another logical connective, the implication, and a third variable, alarm. Here's yet one more. Not burglary and not earthquake implies not alarm. So again, now we have the negation, and so it's pretty simple. More formally, a propositional sentence is formed from a set of variables that you start with, let's say P1 through Pn. These are called Boolean variables or propositional variables. Their values are true and false. And you basically compose sentences simply like this. So in the box there, every proposition or propositional variable is by itself a sentence. If alpha and beta are sentences, then you can just compose them. You negate one, you can join them, you disjoin them, and so on. So it's really a very simple definition of syntax. Now, realize this. This is for now. I just want you to remember. How many know this, by the way? That alpha implies beta is just the same as not alpha or beta. Okay. It may not sound as intuitive. Later, we'll get to it. But now just try to think these are basically the same, which means the implication is really not needed in that particular case, given the other. And here's a simple example showing a circuit on the other side where the wires have been named A, B, X, Y, and C. And on this side, we're actually expressing what we know about that circuit using propositional logic. So the first two sentences talk about the behavior of the inverter. A implies not X, not A implies X. And the last two talk about the behavior of the OR gate. X or Y implies C, and so on. All right. So we call this a knowledge base. Okay, now we get to semantics. So semantics basically means meaning. And the ultimate goal of being clear on the meaning of things, including the meaning of sentences in propositional logic, is to be able to talk about what we call properties of sentences and relationships between them. So a property applies to one particular sentence. The two key properties are consistency and validity. You've heard these terms, even in natural language, right? Consistency or inconsistency is whether something is coherent or incoherent. And I can take a sentence and say, is this sentence consistent or inconsistent? We need to be able to do this mathematically, not based on intuition. Or validity. Validity is when something is always true. It's like a tautology, right? Again, I want to give you something and say, is this a tautology? You'll see, for small sentences, you can probably decide these based on intuition. But more generally, you can't. You need to basically have a mathematical definition for that. Now, this is properties of relationships. When you have two sentences, and probably the most important one is implication. Does this sentence imply that? Is this sentence equivalent to that, and so on? Those look like a lot, and you can come up with a bunch more. But as you'll see, and I hope later, you will come up with these definitions. There's one thing. If we agree on and we explain, and you get it, you can infer all of these definitions yourself. So in fact, that's what we're going to do next. I'm going to get to the central concept on semantics in Boolean logic, and then we'll walk through the exercise of defining these together, right? That would be the reward if you pay attention to the next few slides. Again, just this is meant to say that here's some examples of inconsistent, valid, and things that people can easily tell by visual inspection. But these are examples of things that are not as obvious. For example, that A implies B is the same as not B implies not A, or that these two sentences imply not A. Some of you may know this, some may not. It's not as obvious. Okay, so here's the central concept. And you may have seen this before if you've done it, but if you've done a digital logic course, for example, but from a different perspective, and you may have not paid attention to some of the things we will do here, which are critical. So there's this notion of a world, which is a particular state of affairs in which the value of each propositional variable is known. So in this example that we have, earthquake, burglary, alarm, 3 variables, and each could be true and false. So I have 8 possible worlds. You've seen the tables like this perhaps before, and you've referred to each one of these rows as a truth assignment, or as a variable assignment, or as a variable instantiation. We want to attribute a little bit more to each one of these rows. It's not just a variable assignment. It's a little bit more. It is one way the world could be. Now, what's the significance of this? The significance of this is, if I come to you and I say, I am in world 3, that is the world in which an earthquake took place. There was no burglary, but the alarm triggered. Once I fix that, now something interesting happens. Any proposition, any sentence that I give you cannot be ambiguous anymore. It's either true in that world or it is not true in that world, either true or false. In general, if I don't fix the word, I come to you and say, here's a sentence that says burglary or earthquake implies the alarm. Is this true or false? The minute I fix the world, you must know. It must hold or not hold. Let me tell you why. That's the essence of semantics. As I'll show you in just a second. Okay, we just said that. If, look at the notation, W entails alpha. That reads alpha is true or hold at that world W, or that alpha is satisfied or entailed by that world W. And here's some examples. So look at W4, for example. That entails burglary or earthquake, so that sentence is true at that particular world. Right? Now, here's how we're going to use this. This is going to be the basis of semantics. We're going to do one more definition. You internalize that, then you're ready to do all of these definitions, as I told you, properties and relationships. So, here it is. Look up there. Parse it a little bit first. Mods stands for models. The models of a sentence alpha is what? Is the set of worlds that makes it true or that it holds at, and so on. This is where intuition, philosophy, and mathematics meets in a definition like this. Look what the significance of this definition is. Meaning. When someone says, what is the meaning of something? You think meaning is a big thing, right? It's an ambiguous world. Not here. The meaning of a sentence is a set. You write a complex sentence in logic and say, what is the meaning of that? You bring me back a set of words. Say, this is the meaning of that sentence. How useful is this definition of meaning? You'll just see in a second. Right? So the mods of alpha are all worlds that makes it true. In fact, that set, if you study usually probability in a different context, usually talk about events being a set, they're talking about that set. And we will not distinguish between a sentence and an event, even though they're different creatures, but they refer to each other. Okay, now, here's the first set of observation about this function. The models of a sentence alpha and beta, you can imagine what that is. You take the models of alpha and the models of beta and intersect them. You see why? Because the models of alpha and beta are those worlds at which that sentence is true. So if you take the worlds at which alpha is true and the worlds at which beta is true, and you take the common elements, those are the ones that make both alpha and beta true, right? And the second one is mods of alpha or beta is the union. So on that side, there is a sentence. On that side, we're doing sets, right? Union. And the mods of not alpha is just the complement of the mods of alpha. So if you look at the set of worlds and you pick any alpha, it's dividing that set into two. With this is what people call also compositional semantics. That is, you give me a Boolean sentence, say, what's the meaning of that? Or what's the models? I can break it into pieces, and I find the meaning of each piece, and then I combine them. Right? I don't know. Do we have any linguistics folks here? We do. Right. So, like natural language does not have compositional semantics. In that sense, you basically cannot take individual meanings and combine them, and so on. Okay, so this is one thing you need to. And if you look at your chapter, there is tons of concrete examples there. Okay, so just showing you examples of, here's earthquake, here's the models of earthquake, models of not earthquake, I just complement the first. The nice thing about these equations is, if you know the models of individual variables, which is very easy, right? So if you take earthquake, what are the worlds that makes it true? That's easy. If you have those, that's it. Together with these equations, you can find the models of any complex sentence, correct? You basically use this recursively, and eventually you end up with variables, and you pull their things. So in fact, you already have a simple procedure, very simple to implement, that will allow you to find the models of any particular sentence very easily, using these equations and the boundary conditions of what worlds make certain variables true. Now, first, any questions? Before now, I'm going to ask questions. You're going to tell me. You're going to define consistency, validity, and all of these things. That's it. This is the core of semantics. Any questions? Okay. No. Okay. Who wants to do this? Consistency, a sentence is consistent means coherent. Yes. If there exists a model, there must be one state of the world that makes it true. Then we'll say it's consistent. If there is no world, no truth assignment that will make truth inconsistent, and in our set notation, it would be just this. There's at least one world at which alpha is true, that the models of alpha is not empty. Otherwise, we say that it's inconsistent, and that is the models of alpha is empty. People sometimes use the symbol false to denote a sentence which is unsatisfiable. So there's satisfiable, unsatisfiable, consistent, inconsistent that are interchangeable. We know about SAT, right? The problem of SAT, it's this. I just give you a sentence and I say, is it satisfiable or not? There's a whole industry and conferences and quite a bit of very bright researchers dedicating their lives to this problem, computationally, right? To try to scale to big things. And you'll see why in a little bit. Because we're going to define all of these other relations, and you're going to see that they can all be reduced to SAT questions. So if you know how to do this efficiently, you can do a lot, actually, right? So, okay, validity. Validity is a tautology, something that's vacuous, something that is always true. What's the definition? It's true at every world. So basically, we're going to use this omega to mean all worlds, and yes, it is basically as simple as this. It is true at every world. Yeah. Okay. Sometimes people use the symbol true to refer to a sentence that is valid. right? A simple valid statement is A or not A, right? It's always true. Here's a notation in logic. Second line. You write this entailment guy and put an alpha. That means alpha is valid. This entailment operator, usually you put something before it to say that thing implies this guy. So when you don't have anything there, that means it's always true. You don't need anything for it to be true. It's always true. That's notation. Okay, so a logical property applies to a single sentence, while a logical relationship applies to two of them. So now we're going to look at a bunch of logical relationships, and again, you're going to help me with that. We're going to start with the simplest and end with the most controversial one. I told you what the simplest is. You want to guess what the controversial one is? Okay, we'll leave it a surprise. So, sentence alpha and beta are equivalent. The same words, the same mods, right? They're true at the same set of words. So you can write things differently. You can give me one sentence and another sentence that looks differently, and you look at it and say, oh, they're saying the same thing. They have the same meaning. What does that mean? They're true at the same set of words. Their mods is basically the same. That's the definition. That's what it means for two things to mean the same thing. See now the usefulness of this notion of a meaning as a set. That includes, for example, alpha implies beta. Not beta implies not alpha. Those are the same. They have the same meaning. Okay. Have we heard of the relationship mutually exclusive? Alpha and beta are mutually exclusive. Have we heard that term to start with? Right? It comes up a lot in probabilistic reasoning. Intuitively, what does it mean? No, that's not intuitively. I already polluted you with mathematical language. I want intuition. Suppose you didn't come to this class today. Mutually exclusive alpha and beta. Don't say world. They can't happen at the same time, right? They can't happen at the same time. So they cannot. So the mods of alpha intersection the mods of beta is empty, right? There is no world that makes both of them true. You good? Mutually exclusive. There is a way to draw. I'm still not familiar with that. If I had a whiteboard, I would do Venn diagrams, right? And basically, the sentence is a circle set, and then those two guys would be disjoint sets. The circles will not overlap. Okay, guys, two more. Have we heard of exhaustive? Alpha and beta are exhaustive. You probably heard mutually exclusive and exhaustive. They usually come together. But let's do exhaustive. What is exhaustive? Okay. I'm too mathematical. That's good. I want you to do this eventually. I was trying to go for intuition, but yes. If you look at the models of alpha, the models of beta together, they cover everything, right? Exhaustive, that means they cover every possibility. Now, when you do mutually exclusive and exhaustive, let's say you can do this for three guys, right? Alpha, beta, and gamma. And when you say they're mutually exclusive, that they never overlap, exhaustive, they cover anything. So if alpha, beta, and gamma, when you do Venn diagrams, they end up partitioning the set of the worlds, right? So the set of worlds, one component is alpha, another is beta, and another gamma. They don't overlap, but they cover everything. Now this is the last guy. Alpha implies beta. Alpha implies beta. Implication. Yes. Once again? Good. You gave me the intuitive answer, and that's correct. I want you now to translate it mathematically. You'll get your turn. Go ahead. So now I want you to use mods. Mods of alpha and mods of beta. How do they relate? Okay, I will have to focus the answer. Let me do the following. Now we have a big population, so this is interesting. There's two answers. It's going to be containment. So the mods of alpha are contained in the mods of beta. So remember, the small guy is the alpha, the big guy is the beta, or the other way around. So alpha, beta is A, beta, alpha, I'm trying to emulate a whiteboard. Beta, alpha is B. Who says A? And who says B? More A, small b, but still A plus B is a very small fraction of this class. Can we try again? There's no penalty to this. There is a lot of cameras, but none of them are really pointed at you. They're all pointed here. So no penalty. How many say A? Much better. How many say B? Okay, it is indeed A. And that sounds somewhat counterintuitive at some level, because when you say A implies B, that means A carries more information, right? It's hard to believe that more information is a smaller set. But actually it is, and you'll see why. And this is another insight that I want you to come out of today with. This is a big deal. That when you look at sentences from a circle point of view, smaller is better. Right? A smaller set of words is better in the following sense. You'll see it now next. So here's the definition. Alpha implies beta is, mods of alpha is a subset of the mods of beta. And we're getting to that point in just a little bit. Just notation, that guy up there says that alpha is true at that particular world. It's an overloaded symbol in logic. So you use it that way, you use it also this way. Alpha implies beta. So as you can see on this side, you can either have a world or a sentence. That's okay. And in your book, it doesn't dance like that. But okay, so some equivalences that you may need to be aware of. I think you know most of these guys, so this should be not hard to follow. But check it out in your book. Some of them, it's good to be fluent. You don't want to be thinking about some of these things. There is also this table, which shows how imply, equivalent, mutually exclusive, exhaustive, all can be expressed as satisfiable and valid, but using different sentences. So look at the first guy. Alpha implies beta is the same as alpha and not beta is unsatisfiable. Now that is called the refutation theorem in logic. You've used it all the time. Okay, now it says, well, no, I didn't do logic. I didn't use it. You did use it. In all likelihood, maybe even in high school. Anyone has any clue where this may have come up? Proof by contradiction. Exactly. You know what you do is you say, prove that beta follows from alpha. You say, assume alpha, assume the negation of beta, contradiction, therefore beta must be true. You've done this, right? That's this guy. And that's actually the way set solvers gets used today when they prove implications, for example. They take beta negated, add satisfiable. And you can check the other guys as well. And by the way, you don't need both of validity and satisfiability. Correct? Okay, let's do this exercise. Okay. Some people are not good with negations and double negations. I'm one of them. So I'm challenged by the question that I'm going to ask you. But alpha is valid. Someone doesn't have a validity box, has a box to do satisfiability. Then comes to you, someone says, I want to test whether alpha is valid. How do you use your box to do that? The box does satisfiability. Alpha is valid, that means covers everything. If that was the case, the negation should be unsatisfiable. So I negate, and I use the set box. Right? So you really just need satisfiability in this case. But don't be fooled by that, because where you may get a hit is when I'm doing, let's say, alpha and beta, I want to do implications. Alpha may be simple and beta may be simple. When I make it into alpha and beta and send to a sad box, I'm not sending now alpha and beta alone. I'm sending a more compound sentence, right? And sometimes, depending on what that box expects in terms of format, that conversion may blow things up. So just a side comment for people. Okay, let's go to this last part, which is the other insights I want you to see. Look what happened, which is the idea of smaller is better when it comes to knowledge. That is, the smaller the set of words, the more you know. More you know. Someone communicates to us the following sentence, alpha, which says, earthquake or burglary implies alarm. What happened here? When I'm starting with a blank state of knowledge, every world is possible, 8 of them. Someone comes and says, no, alpha, and I accept it. By accepting it, we are considering some worlds as impossible now. We are throwing out some of the 8 worlds. Which ones are we throwing out? The ones that make that guy false. We're only keeping those guys that make this guy true. Those happen to be 1, 3, 5, 7, and 8. Our state of knowledge now is a set of 5 worlds we threw out. Okay, now you get it. What is the process of knowing? It is a process of throwing out possibilities, eliminating possibilities. When you had 8 worlds, you said it could be this or this or this or 8. And I've learned, says, no, it's only these 5. You learn more. Okay, what's the ultimate state of knowledge? One guy. Now you got to be careful. If you overdo it, what happens? You know too much. You eliminate all of them. What do you get? State of inconsistency. Right? So it's 1, not empty. Empty is too much, knowing everything and its negation. Right? So that's an incoherent state. Okay, so let's see it concretely. So here's alpha, here's the worlds, and then if you look at the set of worlds, 8 of them, and now you have possible, impossible, we mark them yes, no, and that's what this guy did. It just did this marking. Now, we get a new piece of information. Someone says, okay, I know one more thing. Earthquake implies burglary. That's beta. Now, the worlds of that guy are 1, 2, 5, 6, 7, 8. What's our current state of knowledge? Is the intersection. Mods of alpha and beta, so now it's 1, 5, 7, and 8. We dropped 1 more. Look what interesting what happened here. Only 1 was dropped. Now, that guy, 1, 2, 3, 4, 5, 6, it actually drops 2. One of them was already dropped by the previous guy, so it didn't add that piece of information. That piece of information was shared. So now we're down to 4 of them, and learning the new information beta has the effect of ruling out world 3 in addition to those. Okay, now I have a question for you. If we do this, let me see. We can go home. As I give you more information, you have the set of worlds. It's either shrinking, it's becoming smaller. It's possible it could be the same. That is, it's already this set. I give you some information, it doesn't change. What does that mean? I have 2 questions. That new information is already implied. It's not adding anything. If it didn't eliminate a new world, that means I already know it. That means it's already implied by what I have. Okay. Now you shrink and adding more information, it shrinks. What did we just prove? Monotonicity. That's why logic is monotonic. Remember, what's implication? Alpha implies beta, alpha, beta. If you keep adding to alpha and it keeps getting smaller, it will never stop implying alpha, beta, right? And that's indeed the property of monotonicity. You just proved it. You can look at it in set notation. If alpha implies some sentence gamma, then mods of alpha is a subset of the mods of gamma. Since mods of alpha and beta is also a subset of mods of alpha, then we have mods of alpha and beta implies that. We proved monotonicity. Listen, I should have done this before we started. I should have given you 2 slides of exercises, prove validity, prove this, prove monotonicity, and you looked at them. It's interesting that you break into all of these by 1 definition and 1 insight. And you can do more stuff, right? So pick in the book some exercise. It is, the point, it's worth it. This notion of a world and that notion of mods, internalizing and having very good intuitions, it's one of these notions that really pays off a lot in terms of abilities on what to do. Okay, and here's the visualization using Venn diagrams of the relationship between 2 sentences, delta and alpha. The first one is where delta implies alpha. The second one is where delta implies the negation of alpha. And the third where we don't know. There's no relation. It doesn't imply alpha, doesn't imply not alpha. That's actually we're really done. There's just a few things on notation. Let me just do them because I may even repeat them next time. This is important. You may multivalued variables. So everything we did now is propositional. So a variable is true or false, right? Sometimes you have like alarm. And you want to say not the alarm triggered or not, but you want to say the alarm triggered low, triggered high, or it's off. 3 states, right? That comes out a lot. There is really no conceptual difference in this case. Meaning, instead of talking about alarm being true or false. By the way, when a variable has only 2 states, you don't need to mention the value explicitly. We write alarm to mean alarm is true, and then we write negation alarm to mean alarm is false. So we have this luxury of dropping out the explicit reference for the value. The only difference is, if you have more than 2 values, now you have to be explicit. So if you have alarm, you have to say alarm equals high, alarm equals low. Before, instead of saying burglary equals true, I could just say burglary. And the understanding here, it means true. If I want to say it's false, I put a negation. Okay. What does that mean? Everything is the same, except that the notion of a world looks like this now. Earthquake 2 values, burglary 2 values, but now alarm 3 values. So now I have 12 worlds instead of 8. Does that make sense? Nothing else changes. And don't confuse this with what people call multivalued logics, because in the history of AI and science, people talked about what they call multivalued logics, where you don't have just the values true and false when talking about sentences, but you can have multiple truth values. This is not it. In this case, we still have for a sentence either true or not. We're just talking about the variables themselves. It doesn't change anything. But now you can write sentences like this. And the relationship between a world and a sentence is the same. And we will do that a lot, because when we do probabilistic reasoning, discrete variables, multivalued, are common, right? Not binary. The other notational thing is, this is now stuff that's used in probabilistic reasoning. We use variables, big letter, to talk about variables, and small letters to talk about their values. So you would write big A equals small a. Now, if you do it in logic, look what it's going to look like. Big A equals small a, and big B equals da 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 da. Okay. Probabilistic reasoning is a nice way of doing it. You just write small a, small b. It's right there, first line. We will use small a, comma, small b, comma, small c. That's it. To mean that big guy. What's happening here? We're dropping the reference to variables, just using their values, dropping the equality. We're replacing ands with commas. They do it a lot in probability. Stare at this first line. It's important. It's going to be everywhere. That's what people use in probabilities. You can write probability of that guy on the side. Very wordy. Or you write probability of small a, comma b, same thing. That's the notation that's used in probabilistic reasoning for a good reason. It's much more concise, right? We're good? Okay, I think this is enough. We'll see you on Thursday. Thank you.